In this problem, steam enters a turbine, let's say at state 1, and the inlet conditions, the turbine operates at steady state, and the inlet conditions are given, and it leaves a saturated vapor at 4.5 kPa. So I have drawn the two pressure line, constant pressure lines, and state 2 is what I'm calling the isentropic state. 1 to 2, entropy remain constant. This is the ideal turbine, reversible turbine. And the actual exit state, which will share the same exit pressure of 4.5 kPa, may have a different temperature and other properties. So 1 to 3 is the actual turbine, and 1 to 2 is my isentropic ideal turbine. And we have been asked to find the turbine output. So obviously the output from the turbine 1 to 3 and the rate of entropy generation. So therefore you have to do an entropy analysis again for the actual turbine. And the isentropic efficiency is, of course, the ratio of power output between the actual and the ideal turbines. Again, open devices operating at steady states are discussed in chapter 4 in your textbook and module 4 throughout test. So let's go and launch a suitable TESTapp. I have already logged in as a student in different tabs here. So you go to the TESTapp page, and obviously this is a problem of system analysis, open system involving steady state. And if we follow the generic branch, single flow system is what we have. There is only one inlet, one exit. And finally, it's a steam turbine. So PC model where phase can change is our model. We go to the leftmost tab to launch the app. So first thing first, we go to the I/O panel and start entering the given variables. So for instance, so we write a comment, given values. So for example, P inlet is given to us, P inlet in kPa, or I think it's given to us in MPa, is 6. Likewise, all the other given variables I've already listed here. And so just listing here is not enough. We have to click the calculate button so that they are registered. So now the inlet, the given information can be understood or transferred to any other panel. So in the state panel, if I go and say inlet pressure is equal P1 MPa, but notice I must select MPa from here. Only then it will make sense. If I do a calculate, you can see, wait a minute, it's called P inlet MPa, that's why so let me correct that, P inlet MPa. Now if I move the pointer over, and you can see in this zone, you can see the that P1 equal P inlet MPa equals 6 MPa. So likewise, we can transfer all these variables that I know for state 1 and state 2, and state 3. That's what I have done in this tab. So see, P1 is P1 inlet MPa, T1 is T inlet, P inlet MPa, and T inlet degree Celsius. And m dot 1 is m dot that is given to us in kg per second, which is 5 kg per second. State 2 is an isentropic state, so exit pressure is the same, and entropy is set to equal entropy 1. And of course, mass flow remain constant. And finally, for state 3, again, the pressure is the same, and we have been given a quality X3, which is known. It's saturated vapor, so X3 equals 1. We can go to the graphics panel to make sure they make sense. You can see the states 1 to 2 must be isentropic, and you can see 1 to 3 entropy has increased, is the actual device. In the device panel, we set up the ideal and actual device the following way. State 1 is my inlet, state 2 is my isentropic exit, and it's a adiabatic turbine. So therefore, a calculate produces the power output, etc. And for actual device, it's state 1 to state 3. And again, it is also adiabatic, so Q.3 is 0. If I, wait, it should be device 2, I'm sorry. So device 1 is the isentropic one. Let me do that all over again. State 1 and state 2, Q dot equals 0. Power has been calculated. And device 2, we have state 1 and state 3, and that's the actual. So notice that the actual power output is less than isentropic power output. Okay. So now that we have calculated the devices, we can come back to the I/O panel. We know all these values now. So for example, now it's time to find the answers. So we can say part A, what is the power produced? Power produced is what? Is power in kilowatt is W dot external 2, because the second turbine, the second device is the actual device. So I have completed, I thought I completed yes. So instead of power output, I call it turbine output here. And this is in megawatt, so I divide by 1,000. And entropy generation rate is, of course, S dot gen 2. Again, 2 refers to the second device. And the efficiency of the turbine, isentropic efficiency, is the second turbine, which is the actual turbine, divided by the work output of the first turbine. That's the answer to my part C. I multiply by 100 to get it in percent. Again, to see the output, we can just expand this output area. So you can see all the answer to the problem is right here. And in the top panel, if we do a super calculate, it will clean up all your codes, and you can see them here. These are the test code. This is what we entered, and these are the final calculations.